Okay, let's dive right into this explainer and tackle what is honestly one of the most foundational concepts in all of computer science. Today, we're opening up a fascinating chapter on exactly how computers bring order to total chaos. We're going to explore how machines take completely jumbled data and organize it, and perhaps more importantly, how we actually measure the efficiency of the methods they use.
To really get why this matters, can you even imagine the absolute agony of trying to find one single word in a completely unsorted dictionary? I mean, if the words weren't in alphabetical order, you'd literally have to scan every single page, line by line, until you just happened to stumble upon the one you needed. It's a nightmare, right? And that establishes exactly why organizing data is so incredibly critical. Sure, you spend some extra time ordering things initially, what computer scientists call overhead, but it is absolutely worth it compared to the sheer panic of finding an element in a completely unsorted list.
We apply this concept literally everywhere in the real world. We use sorting for everything from finding dictionary definitions, to arranging seats in an exam hall by roll number, to simply lining up students based on their height. At its core, sorting is just the process of ordering a collection of elements into a particular sequence, whether that's increasing, decreasing, or alphabetical.
So here is our roadmap for today's chapter. We're starting with the power of sorting, then we'll meet our three algorithm contestants, bubble sort, selection sort, and insertion sort, before we face the ultimate judge, time complexity.
Let's start with Section 2, Bubble Sort, bubbling up.
Let's meet our first contestant. Now, it's a bit clumsy, sure, but it is very straightforward. The core personality of bubble sort relies entirely on just looking at two side-by-side items and swapping them if they're out of place. It essentially traverses the list step by step, taking pairs of numbers and asking a really simple question. Hey, is the first number bigger than the second? And if it is, they swap places.
In every single iteration through the list, which by the way we call a pass, the largest remaining element is identified and essentially allowed to bubble all the way up to its correct position at the far right. And because that largest element is now locked into its final sorted place, the algorithm just ignores it in the next pass. So the unsorted portion of your list is getting smaller and smaller every single time.
Now the blue highlights here brilliantly track those exact comparisons, while the green highlights show the elements perfectly locked into place at the end. In pass 1, you can see the number 13 continually swapping to the right until it hits the end. And boom, it turns green. Then in pass 2, the number 8 does the exact same thing. It just keeps bubbling those maximum values to the right until the whole list is completely green.
So bubble sort is constantly forcing those massive items to the right side. But our next contestant takes the exact opposite approach.
Which brings us to selection sort, the minimum.
Now this is a much more meticulous method. Instead of just blindly swapping neighbors, selection sort scans through the entire unsorted portion of the list with one goal: find the absolute minimum value. Once it finds it, it swaps it directly into the first available position on the left to start building a sorted pile.
Just visualize an invisible boundary line shifting rightward as the sorted list grows and the unsorted list shrinks by one item each pass. The left side holds your perfectly ordered items, and the right side is that chaotic pile you are still sorting through. It just keeps repeating that scan and swap until every single element has been selected and moved.
You can vividly see the absolute smallest elements being selectively plucked out and permanently locked into that left-hand side. The arrows track the comparisons, finding that absolute minimum value like the -9 in the first pass and swapping it straight to the very beginning. And once it's there, it's considered part of the sorted list and is never checked again.
So, compare that massive, wide search to our third contestant. Selection sort has to scan the whole unsorted list every time. But our next method behaves exactly like you probably do when you're organizing a hand of playing cards.
Yup, it's insertion sort playing cards.
Instead of hunting down the absolute minimum across the whole list, insertion sort just grabs the very next available element and figures out exactly where it fits among the already sorted items. Seriously, imagine picking up a new playing card from a deck. You look at the cards already in your hand from right to left, and you slide that new card into its perfect sequential slot.
It actually looks backwards through the elements you've already sorted. It shifts the larger numbers to the right just to open up a perfect, snug little gap for the new insertion. This means every time it picks up a new number from the unsorted side, the sorted side briefly expands and makes room for the new arrival.
Watch how the arrows are dragging the current element backward, sliding it right past the larger numbers until it finds its rightful sorted home. Take pass 2, for example. The number 1 is compared against 13, 8, and 7. They all shift to the right, creating a space at the very beginning for the 1 to drop into. It's an incredibly elegant approach, especially for partially sorted data. But all 3 methods do sort the list, so how do computer scientists actually judge which one is best in the real world?
That brings us to Section 5, the ultimate judge, time complexity.
They look at time complexity. They want to know, does the processing time stay constant, scale linearly, or completely explode quadratically as the dataset grows? If an algorithm has no loops, its complexity is 1, meaning it takes the exact same amount of time no matter what. A single loop makes it linear, or n, meaning time grows at the exact same rate as the data. But a loop within a loop, that makes it quadratic, or n squared.
Well, when we peek at the underlying Python code from this chapter, for all 3 of our contestants, they actually share a common trait. One loop nested inside another. They have an outer loop to track the number of passes and an inner loop to handle the specific comparisons and swaps for that pass.
And because of those nested loops, all 3 of these foundational algorithms hit a wall. They share a quadratic time complexity, meaning the time it takes squares as the data grows. Now, for a small list of 6 or 10 elements, like in our chapter's examples, the difference in processing time is basically unnoticeable. They all perform just fine.
Which leaves us with a pretty massive question. If an n-squared algorithm starts to choke as data gets huge because the time it takes grows exponentially, what happens when the list isn't 10 elements long but 10 billion elements long? How did giant tech companies manage billions of records without their servers just melting down? Well, that is the real puzzle computer scientists have to solve when moving from the classroom into the real world.